you about what the molecule looks like. So for that regard, on top of the Lewis dot diagram, we want to introduce the new model, which is called the valence shell electron pair repulsion theory, or abbreviated in VSEPR. So what VSEPR is doing is telling you information about the shape of a molecule. Again, we're in the classical domain. Right now we're looking at chemical bonds or just shared electron pairs. The idea is quite simple for VSEPR. Here we're just talking about electrons or charged particles. So naturally, when you have charged particles of the same sign, right, you have negative charged electron pairs in close proximity to each other, naturally, these electrons will repel each other. What that means is electrons that surrounding a center atom will want to stay as apart from each other as possible. So we'll take a look at some of the examples in how this electron will behave in a three-dimensional space, and then we'll do some problems together. All right, so the idea here is simple. It's because we're treating electrons as just negatively charged particles, these negatively charged particles want to stay as far away from each other as possible. So with that in mind, we can come up with a prediction in where that electron pair will likely locate in the three-dimensional space. And that's called electronic geometry. Basically, that describes the position of these electron pairs around a center atom. So right now, let's just look at how these electron pairs will orient itself in three-dimensional. There are several possibilities. Let's start by thinking about just two electron pairs around a center atom. All right, so the black dot here means that's my center atom. And then the smaller purple dots are hypothetical electron pairs around it. So what it means, electrons want to stay as far away from each other as possible. And these gray ones are just distance between the electron and the nuclei. We're assuming that's a constant distance. It can get more complicated, but right now this is our simplified model. So in the two electron pair scenario, it's quite simple. These two electron pairs want to stay as far away from each other. So this is what we call a linear geometry, where the electrons basically stays on two sides of your center atom. All right. Moving on to the next one, now we have the two electron pairs. It's straightforward. They just want to stay as far away from each other. That's a linear geometry. If we have three electron pairs, again, electrons want to stay as far away from each other as possible. So here we have a trigonoplanar geometry, and the angle here is 120 degrees. So far we're all on the planar world. Things get a little bit more complicated when we move on to the four electron pair scenario. So in the four electron pair scenario, what we're having is what we call a tetrahedral geometry, which is a little bit weird. Let me just walk you through. So first of all, in the tetrahedral geometry, the angle between these electron pairs are all 109.5 degrees. So where that 109.5 comes from is if you imagine a cubic, right? So that's a cubic, and then you put the center atom in the middle. So that's where your center atom is. And the best way to orient those electron pairs so they're as far from each other as possible is to put those electron pairs on the corner of that cubic. So the consequence here is at the top two corners that are diagonal to each other, they're as far away as possible. And on the bottom, it's on the other two corners. So that's how scientists came up with the tetrahedral geometry, and that's where that 109.5 comes from. So that's the 4 coordinated. We put the center atom in the center, and then we put the electrons on the corner of that cubic, that hypothetical cubic. Moving on to the 5 electron geometry, where we have the trigonal bipyramidal. So why we're calling it a trigonal bipyramidal? So now the electrons, now we have 2 different types of electron. On this blue triangle here, these are called equatorial positions. And then the bond angle between all these electron pairs are 120 degrees. But again, now we're in the 3-dimensional world. So you have 2 more electrons and on top and bottom of that triangle. Imagine this paper, that's like your triangle. And then on top and on bottom, you have 2 more electron pairs. Those 2 electrons are my axial electrons. And then the bond angle between an equatorial electron pair and the axial electron pair is 90 degrees. With me so far? All right. And then the last one we'll be talking about are 6 electron pairs. They're called octahedral. It's actually a little bit more straightforward than the 5 coordinated one, because now you only have 1 type of electron. No matter how you rotate it, the angle between all these electron pairs is always 90 degrees. So these are just the fundamental electronic geometry and how we came up with these electronic geometry. Just you look at the electron pairs and you use a little bit of the math and topology to figure out the orientation of the electron pairs. And again, people generally speaking using VSEPR to give you an estimate of the 3-dimensional molecular geometry of a given molecule. So let's do some examples and see how does the VSEPR actually apply to real molecules. Before we do that, I want to go over the procedure to use VSEPR to determine the molecular geometry. It's actually just 3 steps, a little bit shorter than the Lewis dot diagram. First step, you draw the Lewis dot diagram. So again, Lewis dot diagram gives you basic connectivity of atoms in your molecule, and also it requires your atom fulfills the octet rule. Second step, you calculate something called a steric number. So steric number is a little bit different from the number of chemical bonds. So steric number only counts the number of things, whether it's an atom or a lone pair that's surrounding a center atom. So that's the steric number. So for example, if we have a acetonitrile, all right, if we look at the acetonitrile here, let me just zoom it out. In here, surrounding that nitrogen, we have 2 things, right? We have 1 carbon atom and 1 lone pair. So 1 atom plus 1 lone pair. So steric number equals to 2. Surrounding that center carbon, that's the same idea. Just now we have 2 atoms. So the steric number also equals to 2. And for this carbon here, we have 4 atoms surrounding it. So we have 3 hydrogen and 1 carbon. So we have 4 atoms surrounding it, and the steric number equals to 4. So just counting the number of, either it's atom or lone pair, just counting the number of things surrounding the center atom. We'll see some more example later on. And then you just refer to the table. So depending on how many lone pair you have and what is the steric number, you can refer to the table to identify the geometry of your molecule, the molecular geometry. And one thing to keep in mind is that the lone pair, because it's not bonded, the lone pair electrons will take a little bit more space in your three-dimensional space. Let's do some example questions together. And I'm going to keep this file here for you. Okay. We all know the first step is drawing the Lewis-Dot diagram, so I'm just hiding it. Again, the second step is figure out the steric number, and then we refer to the table and try to figure out the molecular geometry. I think I already have the answers here for some reason, but it's okay. We'll do it together. All right, so ignore those red answers on the table, but let's just do it together and see how we actually work it out. First thing, water. If we draw the Lewis-Dot diagram of water, H2O, we can have the oxygen in the center. And then apparently surrounding that oxygen, we have two lone pairs. You can double check and make sure, hey, do we have octet rule fulfilled for all the atom in my Lewis-Dot diagram? And then we look at the center atom. Around that oxygen, we have two lone pair, two atom. That gives you the steric number equals to 4. So the steric number equals to 4, and then the number of lone pair equals to 2. That ends up to be a bent geometry. Or if we draw it out on paper, we draw it as a bent geometry. What it means is we have hydrogen, oxygen, hydrogen, and then the two lone pairs. One thing you would be asked to do is to label the bond angle. For example, in this case, in the table here, we're saying that bond angle is going to be smaller than 109, which is the tetrahedral bond angle, if you remember. And this is because our lone pair electrons will occupy more space. But this information you can get from the table, but the theory behind that number being smaller than 109.5 is because the lone pair electrons on the oxygen occupies more space. All right? Okay, next up, BH3. So, BH3. This one, again, when drawing a Lewis-Dot diagram, we don't have much option. You just have the boron in the middle, and then hydrogen surrounding it. Note that your BH3 doesn't really fulfill the octet rule. Boron only have 6 electrons surrounding it. So that's one of the scenarios where you're violating the octet rule. Boron just does not have enough electron around to surround to get that octet rule fulfilled. It's more or less acting like a metal anhydride, like NaH or lithium H. It doesn't fulfill the octet rule whenever you don't have enough electrons around. Nevertheless, let's look at boron and try to get an estimate on what the molecule looks like. So surrounding that boron, we have 3 atoms, which means your steric number equals to 3. In the next step, refer to the table. Steric number equals to 3, lone pair equals to 0. I mean, I already write the answer key on there, so it's a trigonal planar. And we can draw it accordingly, and then label the bond angle accordingly. All right. Next up, CH4. You see the trend here. And first, we draw the Lewis dot diagram. And we see in the center, the atom is 4 atoms surrounding that carbon. Steric number equals to 4 and 0 lone pair. Right, and we read the table, steric number equals to 4. There exists 0 lone pair, so apparently that's a tetrahedral geometry. So we can draw that tetrahedral. So the way we draw a tetrahedral geometry is use wedges and dashes whenever you have atom that's in and out that surface. So that's why I'm going to just draw it with you, and you want to take some time, practice your drawing, because you're going to see the tetrahedral comes out again and again. So the way we draw it is, again, we put the carbon in the middle. And here, whenever you have a normal line between these 2 hydrogen, these are on the plane of my paper. And when you draw it with a dashed line, so this tells you the hydrogen is beneath the surface. And then when you draw it with a wedge, this tells you the hydrogen is above, is pointing out to you. Or the other way to think about it, right? This is the surface, and you define it by these 3 points, right? H, C, and H. These 3 points defines the surface, and then the dashed hydrogen is going beneath the paper, and then the wedged hydrogen is coming out towards you. So you'll see these wedges and dashes. Well, not only in the tetrahedral, but in other molecular geometries. Just get familiar with it. Yes?
Does it matter where you put the wedge and the dash?
So that's a very good question. The question is, does it matter where you put the wedge and dash? For now, for CH4, it does not matter because the 2 hydrogen are equivalent to each other. We can't distinguish it from each other. But when you go to organic chemistry, you will soon learn stereochemistry, and you'll see when you have different groups, when you have a stereo center, then it does matter. So for this class, we're not talking about stereochemistry yet. So it doesn't matter where to put 2 chemically equivalent atoms with the relative position of these 2 hydrogen. But in the future, they will come important. Yes?
When you're trying to figure out a shape, do you always want to calculate the steric number of the second?
Yes. So for these kind of question, in the exam question or in your Cengage assignment, you'll see we'll put an underline, say what is the molecular geometry around the center atom. That center atom is highlighted or labeled somehow. All right? And let's just move on to do some more examples. I mean, these are not hard. These just takes practice. NH3. So it's the same procedure. We draw the Lewis dot diagram again. We have the nitrogen in the center. We have 3 hydrogen atoms surrounding it. And apparently nitrogen doesn't have 4 octets. We have the lone pair added in. All right, so this is just the common procedure in drawing the Lewis dot diagram. And then we look at it, the nitrogen center. There exists 1 lone pair and 3 atoms around it. So my steric number equals to 4. Steric number just counting the number of things around it. We refer to the table. I already labeled it. Steric number equals to 4, lone pair equals to 1. So that's called a trigonal pyramidal. Right? That's a new geometry. That's not an electronic geometry, but it is a molecular geometry. So that's my trigonal pyramidal. And what it looks like is you have the nitrogen in the middle, and then here you have the lone pair on the top, and then the hydrogen. So these three groups define your plan of paper. And then you have two more hydrogen. One come out, that's wedged, and one goes in. And when you're labeling the bond angle here, normally we expect that bond angle to be around 109.5, but because the lone pair takes more space, the bond angle of that H and H bond is going to be smaller than 109.5 degrees. All right, so the procedure is almost the same. You draw the Lewis dot diagram, identify the steric number, and then search for the table to find the name of that molecular geometry, and then you draw it accordingly. Okay. We got two more examples. PF3. So PF3, this is actually, when you draw the Lewis dot diagram of PF3, you'll soon recognize this is another violation of the octet rule, because the center phosphorus is binded to 5 fluorine atoms. And apparently it's violating the octet rule. And it is possible because phosphorus, that's our period 1, 2, 3, period 3 element, has a potential d orbital. So for this class, when we're talking about violation of the octet rule, in typical scenario, your center atom is going to be phosphorus or sulfur, or it's a metal anhydride. So for me, whenever I give a Lewis dot diagram, you can assume it does not violate the octet rule. If it violates the octet rule, I'll make a comment and say, hey, this molecule violates the octet rule for this class. But in general, phosphorus, sulfur, Se, arsenic, these are the elements that tend to violate this octet rule. All right, and now we look at it. What's the shape of this molecule? What's the shape of my PF5? The center atom have 5 atoms around it. And then your steric number equals to 5. We look at it, steric number equals to 5, lone pair equals to 0. That's my trigonal bipyramid. And then the way we draw it is you put the phosphor in the center. And then these are my 2 axial atoms. And then we're going to do 3 equatorial. Whenever you have a dash that's going into the paper, and the wedged, it's pointing towards you. So these 3 ones are my equatorial. And when you're labeling the bond angle between the equatorial atoms, the bond angle is 120 degrees. You want to draw that arrow a little bit more clearly because I don't want to get confused when, like, I don't know what you're drawing. Or for the axial, that's here. Right, because they're different. Make sure you highlight your equatorial atoms and your axial atoms when drawing it. One last example here, SF4. So, sulfur is bonded to 4 fluorine atoms with a lone pair. Again, sulfur is violating the octet rule, and it's okay. It's our period 3 atom. It can violate the octet rule. We look at it. In the center sulfur, we have 1 lone pair, 4 atoms. The steric number equals to 5. And we look at it, steric number equals to 5. We have one lone pair. And I don't have it here, but that's our SF4. And that molecular geometry is called seesaw. It looks like a little bit like a seesaw. We'll draw it together. So what we have is a sulfur in the center. And note that in this geometry, your lone pair is always in the equatorial position. And then the atoms are in the axial position. So here I want to pause a little bit, and you can think about it. Why the lone pair will take the equatorial position, not the axial position? Anyone care to take a guess? So I'll give you a little bit hint. Remember, in this trigonal bipyramidal, right, as we show here, the angle between your equatorial atoms is 120. The angle between your axial and equatorial atoms is 90 degrees. The other piece of information is lone pair tend to take more space. So taking together, because lone pair takes more space, it will occupy that equatorial position that's geometrically more open. It is a little bit further away from other pairs. Right? If you think about it, every equatorial atom, right? So these other two equatorial atoms are 120 degrees away, and the two axial is always 90 degrees to the other three atoms around it. So here I just want to write it down again. So first lone pair, a molecule with steric number equals to 5 always goes to equatorial position. And the reason behind it is because your lone pair takes more space geometrically. Do you have any questions before we move on? Okay, sounds good. Next up, now we know what's the shape of your atom and what's the connectivity of the atom. Remember, we talked about connectivity by doing the Lewis dot diagram, and then we deduced the shape of your molecule using the VSEPR theory. Now the question becomes, and how can we tell if a molecule is polar or nonpolar? We touched it before when we were looking at a diatomic molecule, right? The easy HCl or CO2. HCl is for sure polar, and CO2 is for sure nonpolar because the dipole moment cancel out with each other. And here, let's look at something that's more than two atoms, or what we call polyatomic molecules. So the rule is the same. Dipole moment, the origin of the dipole moment is because your electron negativity between the two atoms that bind together are different. So the electron in that covalent bond is not being shared evenly, right? So the electron is more attracted to the more electron negative atom. So the example we did before is HF, right? So apparently fluorine, that's our most electron negative atom, and naturally your electron is more attracted to the fluorine instead of to the hydrogen. So when we're drawing it, we draw the dipole moment from the partially positive atom to the partially negative atom. Origin of that dipole moment of that polar covalent bond is a difference of electron negativity between the two atoms that are bonded together. That's a bit of the review. So Now we're moving on to talk about polyatomic molecules. We'll use CO2 as an example. So in CO2, the rule I wish everybody to get is that dipole moment of opposite direction will cancel each other out. So dipole moment has a direction, right? We're pointing from the less electron negative atom to the more electron negative atom. So for carbon dioxide, we can draw the Lewis dot diagram. And in here, our carbon center has a steric number equals to 2. All right, remember the steric number, we're just counting the number of groups around it. Whether it's single bond or double bond, it's the same. So around that carbon center, we only have 2 oxygen atoms around it. So steric number equals to 2, lone pair equals to 0. We have our linear geometry that's on the top left corner. And here, if you think about it, the carbon is less electron negative comparing to oxygen. So on the left-hand side, we have one dipole moment pointing from carbon to oxygen. On the right-hand side, we have the same dipole moment pointing from carbon to oxygen. So these 2 dipole moments are effectively the same, because in both cases, we're talking about carbon and oxygen, right? So the dipole moment is the same, just of the different direction, and they will cancel each other out. All right. So since we're here, let's do an additional example. Imagine now, instead of CO2, we're replacing one of the oxygen with a sulfur. And since we know sulfur is less electron negative comparing to oxygen, although it is still more electron negative than carbon, what we're having is the same idea, right? You have the carbon-oxygen dipole moment. It's the same linear structure. But now the right-hand side, this dipole moment will be smaller. So what that means is only part of that dipole moment will be canceled out. And there exists a molecular dipole, means this entire molecule has a dipole moment. And if we draw that molecular dipole moment, it's going to look like this. Right? That's being part of that CO dipole moment is being canceled out by the CS dipole moment, but there exists some molecular dipoles too. All right, with me so far? There are different directions that cancel each other out, but at the same time, we're looking at the magnitude of that dipole moment. It can be partially canceled, ends up to be a smaller molecular dipole moment. Second rule, if you have dipole moment of the same direction, they'll add up to each other. We worked on water before, so I'm just going to draw its molecular geometry. It's a band structure with 2 lone pairs on top. And in this band geometry, now we have 2 dipole moments from hydrogen and oxygen. Oxygen is more electron negative than hydrogen. So naturally, we can draw the 2 dipole moments from hydrogen to oxygen. And this one, you need to use a little bit of a math. So right now, we have 2 directions. Right, you have the x direction and the y direction. So apparently, in each of these vectors, the x direction cancel out, but the y direction are add up to each other. So what it turns out to be a molecular dipole just along the y direction. And whenever your molecule has a non-molecular dipole, or we expect it to have a molecular dipole, we call that molecule a polar molecule. So that's why we always say water is a polar molecule, and carbon dioxide is not a polar molecule. Right, so this is one of the typical application of the VSEPR. And why do we need to know the molecular geometry? It tells you information about whether your molecule is a polar or non-polar molecule. All right, so let's do some practice together. Okay. So, here the question reads, SF6 is prepared from SF4 and F2. In order to, so for these two molecules, SF6 and SF4, can you draw the molecular geometry and circle the polar molecule and also draw the molecular dipole moment of these two molecules? So I'm just going to write out these two molecules of interest because I'm going to scroll down. So the two molecules of interest is SF6 and SF4. And we're drawing their molecular geometry and try to determine the molecular dipole of these two molecules. All right. First thing, SF6. This one we just did before. We have steric number equals to 6. We don't have space for lone pair. So we read the table before we do that. Steric number equals to 6, lone pair equals to 0. That's for sure a octahedral geometry. And then we draw the octahedral accordingly. And remember, whenever you have dashed, that's going into the paper, and wedged, that's coming up towards me. And like that. And whenever you draw the molecular geometry, remember you should also label the bond angle. That's also given in the table. It's a little bit too small, but you should be able to see there's a little 90 there. And that's my octahedral geometry. We have several polar bonds in my octahedral geometry. So every one of these SF bonds is polar, right? Fluorine is our most electron-negative atom. So the SF covalent bond is a polar bond. However, because they all point to opposite directions, right? So these two cancel each other out. These two cancel each other out. And these two cancel each other out. So although we have multiple polar covalent bonds, the dipole moment all points to opposite direction with each other. So the result is SF6 is not polar. Or when we say this molecule is not polar, what we're actually saying is SF6 molecule does not have net dipole moment. So they all cancel each other out. All right, so that's our SF6. And now we're moving on to SF4. Let me move things around a little bit. So, SF4, this one we actually just did in our example. You have 4 fluoride binding to sulfur, but sulfur has 6 valence electrons, so naturally we need 1 lone pair on the sulfur. So this one has steric number equals to 5, lone pair equals to 1, number of atoms equals to 4. We read the table. Steric number equals to 5, lone pair equals to 1. That's our SF4. So that's a seesaw geometry. Likewise, we draw it out. I put the sulfur in the middle. we have the fluorine on both the axial position, and then 2 more on the equatorial position, and the lone pair is in the equatorial position. All right, and remember the reason we put the lone pair on the equatorial position is the lone pair takes more space, and we want it to be more open. Let's highlight the bond angle here. So between the axial and the equatorial, that's slightly less than 90 degrees. And between the equatorial, that's less than 120 degrees. And the reason they're not at that number because your lone pair is taking more space. You can also read it from the table there. So apparently, yes. Yes, so the question is, do we need to know the direction of the dipole? So the answer is yes. You can quickly derive it. Again, the origin of a dipole moment comes from a polar covalent bond, right? When we say polar covalent bond, we mean electron pairs not being shared evenly. The more electron-negative atom attract the electron stronger, makes that covalent bond a polar covalent bond, uneven electron pair sharing. So the direction always points from less electron-negative atom to more electron-negative atom. So for this molecule, if we draw out the dipole moment, I'm just going to all use green. We see that on the 2 axial position, they pretty much cancel each other out. But on the equatorial position, now we have these 2 that partially cancel each other out on this y direction. But on the x direction, those 2 dipole moments will add up to each other. It's pointing to the same direction. So the consequence here is we have a net dipole moment for the entire molecule. Or we say this molecule is polar. All right? I think I have time for one more example. I actually have 2 more examples on the lecture notes, so you can work on the last one yourself. So, second example. Imagine a hypothetical molecule, AH4. It has a tetrahedral molecular geometry. And also, I'm telling you this element A is in period 4. Can you write the symbol of this element A and the electron configuration of A? So this is more of a reverse problem. You're using the similar concept we covered, but it's using it from a different perspective. So the logic flow is AH4 is tetrahedral. You read the table, right? So this is our tetrahedral molecular geometry. And what you can derive is the steric number equals to 4, lone pair equals to 0. What it means is that element is making 4 single bonds with the 4 hydrogen. All right, so it's AH4. And you think about it, it must be a tetravalent atom. So tetravalent atom, that's in our group of carbon atom, which is our group 4A here. So that's tetravalent. That's in group 4A. And then the question also gives you that atom is also in period 4. Let's count it. 1, 2, 3, 4. That's our arsenic. Wait, not. That's our GE, right? So group 4A and period 4. So that's our GE, number 32. That's our germanium. And you want to read it carefully, right? What the question is asking? It's asking for the symbol and then the electron configuration. So you want to write both. So identify it to be our germanium. So the electron configuration of germanium GE is argon, that's a noble gas before it, 3D10, 4s2, 4p2. Right, so it's just, this is one example of, right, it's not just using the concept we learned, It also requires you to know the periodic table, to know the electron configuration. So just another way we can ask a question on the exam. There's one more practice exam on the note, and I think I'm 100% one lecture behind, so I'll need to reorganize my class a little bit. But anyway, thank you very much.